Hello, welcome to Ogo Reviews. In this video, we're going to be looking at atomic structure, just a brief review, and also look at some basic terminologies that are associated with atomic structure. And we're going to further on look at what we call hybridization states and atomic orbitals and things related to the atomic structure. So let's begin by just take a brief review of what atomic structure looks like. So an atom is perceived as having a central nucleus that has protons and neutrons. Now the neutrons, as we know, are neutral. You can tell from the name neutral. Protons are positively charged. You can tell from P is positively charged. And then it is surrounded by electrons, which are negatively charged. These electrons are kept in orbit by the attractive force between the electrons, which we said are what? Negatively charged. So electrons are negatively charged. So there is an interesting attractive force between the nucleus and the electrons that keeps the electrons revolving around in what we call the shells or the energy levels. Now let's take a look at some terminologies that we might want to be familiar with. One of them is what we call atomic number. So atomic number is unique to every element. It is the number of protons that you find in the nucleus of that particular element. Another closely related terminology is what we call atomic mass. So what is atomic mass? Is the addition or the sum of the protons and the neutrons. So the protons and the neutrons make up the mass of that particular atom. The reason is that the nucleus is basically where most of the weight of the atom or the element resides. So we don't really consider electrons, we consider them for reactivity's sake. So the mass of the atom would definitely depend on the protons and the neutrons. And atomic mass is denoted as A, and atomic number is usually denoted as a Z. So on the periodic table for an element X, for instance, you're going to see that the atomic number is always at the bottom as a Z, and atomic mass is always at a superscript at the top left. Now, there's another interesting thing that we realize that a lot of these elements have what we call isotopes. So what are isotopes? Isotopes are the variations of the same element that tend to have different mass numbers. So they do have the same atomic numbers, but then the mass number is different. So what do we mean by that? So isotopes, let's define this, have the same atomic number, so same Z, but different atomic mass, different A. So let's illustrate this with an example using chlorine. Chlorine can present itself as chlorine 35 with atomic number 17 or chlorine 37 with atomic number 17. So as you can clearly see, these two are isotopes because they have the same atomic number but different mass numbers. So if you want to calculate the number of neutrons, which pretty much is just the difference between the atomic number and the mass number, you're going to get 18 for chlorine 35. And if you did subtract 17 from 35, you will get 20 for chlorine 37. So as you can clearly see, the differences in these isotopes is because you have different neutron numbers. Now let's take another example with carbon. So carbon has atomic number 6, and you can have carbon present as carbon 12, carbon 13, and then carbon 14. Now carbon 13 and carbon 14, and all of these are isotopes of each other because they have the same atomic number but different mass numbers. So if you did the same calculation, you will realize that the neutron number in this case will be 6, 7 for 13, and 8 for carbon 14. Now, in relative terms, these atoms are present in different concentrations, or I should say different amounts. So, for instance, carbon 12 is present in about 99% in nature. Carbon 13 is about 1% in nature. and carbon-14 is just present as trace amounts. And therefore, this is what is used for carbon dating. One of the reasons is that it is radioactive, so it's able to emit some radiations, and therefore is why it's used for carbon dating. Now, since we've looked at isotopes, we wanted to calculate the relative atomic mass of atoms. So if you look on the periodic table, you will see that for chlorine, the atomic mass of chlorine is about 35.5. And how do you get this 35.5? You do that because you have to find an average of all the average weight, I should say, the average mass of all isotopes of that particular element. So for instance, we know that chlorine 35 is present in about 75% in nature, and chlorine 37 is present in up to 25% in nature. So if you wanted to calculate the relative atomic mass of chlorine, then you have to take into consideration all the different percentages of abundance. So let's see how that goes. So what we have to do is we're going to say we're looking at 75% of the weight of chlorine 35, which is 35, and then you add that to the 25% of chlorine 37. So to do that, we're going to say 75 divided by 100, multiply that by 35, I should say. Add that to 25 over 100, which is the percentage, multiply that by 37. If you did that, you're going to get 26.25 for chlorine 35 and 9.25 for chlorine 37. When you add this, you're going to get 35.5. So that is how you calculate the relative atomic mass of chlorine. So let's take a minute and look at electron configuration. Electron configuration tells us how electrons are distributed in an atom. In most cases, electrons go into what we call shells or energy levels. Now, energy levels have different subshells, and these subshells have what we call orbitals. So let's look at energy level 1 or shell number 1. So shell 1 has the s orbital. Shell 2 has the s orbital and also a p orbital. Shell 3 has the s orbital, p orbital, and d orbital. Whereas shell 4 has s, p, d, and f orbitals. Now, the interesting thing is that if you look at the orbitals of d and p, they have suborbitals. So d has 5 suborbitals and p has 3 of those. Each orbital can take up to 2 electrons. So what it means is that the d orbitals can take up to 10 electrons. And guess what? The p orbitals can take up to 6 electrons. Because the s orbitals is just one orbital, it doesn't have any suborbital, you always have 2 electrons going into that particular orbital. Let's look at how to draw the electronic configuration for carbon, nitrogen, oxygen, and maybe chlorine. So carbon has atomic number 6, nitrogen has 7, oxygen 8, and chlorine 17. In order to write the electronic configuration of these atoms, you have to understand how the energy levels are arranged and how the orbitals look like. So to do this, usually what I advise is that you draw a box of 4 squares in each one of these. And what you do is you try to enter the different shells. So you see that this will represent shell number 1. This will be shell number 2, 3, and 4. Now, in each one of these, we have 1 S, as we mentioned earlier. For shell 2, we have 2 S, and you're going to get 2 P, right? And you go on to 3 S, and the third shell, you have the S, and then you have the P, and you have the D. On the fourth shell, you have the S, you have the P, you have the D, and you have the F. So to make it easy, what you do is you draw a line from one part of this square to the other part diagonally, and then you go to the next square, you draw that arrow through it, and so forth and so on. So you go through like this. So you get all these arrows going through these orbitals. So now what you do is that you pick each one of the arrows. So you have arrow number 1, you have arrow number 2, 3, 4, 5, 6, and 7. So if you have to arrange these orbitals in increasing order of energy, meaning you're going to start with 1, 2, 3, 4, up to 7, right? Now, whenever you're considering these orbitals, you start from the top to the bottom. So let's see how that would look like. So we will have 1s being the lowest energy. The next orbital will be 2s. And then you go on to the next arrow, which is arrow number 3. You have 2p. Okay, always look at the one at the top before the one at the bottom. And then you have 3s coming in at shell number 3. You go on to the 4th arrow, which starts with 3p and 4s, right? You go to the 5th one, it has 3d and 4p, and goes on and on and on and on like that. But for the sake of organic chemistry, we will restrict ourselves to just these orbitals. So now let's take a look at how the electronic configuration of carbon is going to look like. Now, since carbon has 6 electrons, we're going to try and fill these orbitals with the 6 electrons according to the order that we have it here. So to do that, we're going to start with 1s. We know that it can take up to 2 electrons, leaving us with 4. The next orbital in this order will be 2s, which can also take 2 electrons. Then we go on to the 2p orbitals. So the 2p orbitals has 3 different subshells. It has 2s, 2py, and 2pz. So in order to make it easy, the rule is that all these 3 suborbitals have the same energy. We call them degenerate orbitals. They have the same energy. So what you do is that you fill them up using 1 electron each before. If there's excess electrons left, then you fill each one of them, or you complete the filling of each one of these suborbitals. So since we have only 2 electrons left, we're going to put it in the x and the y, and the p will have nothing, right? So another way to represent this is that in some cases, you can actually make it 2p2, which is also acceptable. Now let's look at nitrogen. Nitrogen will have similar electronic configuration, 2px, 2py, and 2pz. So like we mentioned, you fill in the electrons in each one of these, and that will give us 7 electrons for nitrogen. So all the p orbitals will have partially filled electronic configuration. Now oxygen will have 1s2, 2s2, 2px, 2py, 2pz. We have 4 electrons to go into the p orbitals. You start with 1 in each, and then you start filling it up by completing the orbitals. So we're going to put 2 for the 2x. So that means the 2px is completely satisfied or filled, but the 2p, y, and z are partially filled. Now looking at that of chlorine, chlorine has 17 electrons, so that makes it easy. So 1s2, 2s2, 2p6, we don't have to show all the degenerate electrons. 3s2, because now we are here. We've completed filling all these orbitals. So guess what? At this point, we have 12 electrons, remaining 5. The next orbital is 3p, and we know that the 3p will have x, 3py, 3pz. And these 5 electrons will have to go into these orbitals. So if one goes into each, you still have 2 electrons left. So it means that 2px can have 2 electrons, 2py can have 2, and 2pz will have 1. And that will be the electronic configuration of chlorine. So what is hybridization? Hybridization is the mixing of orbitals, of maybe p and s orbitals, to be able to produce what we call degenerate orbitals that have the same energy. And these orbitals are capable of forming bonds with other atoms. So to be able to understand this, let's take an example with carbon and see how carbon can hybridize its orbitals. Carbon has atomic number of 6. So its atomic configuration or electronic configuration will be 1s2, 2s2, and when it comes to the p, we have the s, y, and the z, right? So there are 2 more electrons that go into the s and the y according to the Pauli's exclusion principle and the Hind's rule. Now the last orbital has 0 electrons in it. Now before this carbon can form a bond, what happens is that one of these electrons will jump into the p or the empty p orbital, and that will mix both the s and these 3 orbitals together, so you produce degenerate orbitals. So if you watch it closely, you have 2 electrons to show all the electrons in their orientation. This electron right here will be able to jump, so one of them will move into this empty p z orbital. And when that happens, now you're going to have a new set of orbitals that is a mixture of the s orbital and the p orbitals. So you're going to have 2s, 2p, s, 2py, and 2pz. So all of these are going to have 1 electron each. And these orbitals will mix together, and now they will have a different look and shape, and therefore we call them sp3 orbitals. So you're going to have 4 sp3 orbitals. So you have 1 s mixing with 3 p's, pretty much 25% s and 75% p. So you have more p character than the x character. So keep that in mind, than the s character. So this gives us 4 kind of bonding orbitals. Next, let's look at carbon hybridization, where only 1s hybridizes with 2 p orbitals. So 2s2, which has these 2 electrons, will be mixing with only 2 p orbitals. So like we mentioned, one of these electrons will move. So before we only have, before the excitation, the carbon atom has only 2 electrons in the p orbitals. So when this electron moves here and messes with just 2 of them, you're going to have 2s, 2ps, 2py, 2pz, and each one of them is going to have 1 electron. But then it's only 2 of these orbitals that will mess with the s orbital. So when that happens, you have 1s messing with 2 p's, and that will give us 2p orbital hybridization. And it will leave out one of the p orbitals. It can actually be used for what we call pi bonding. We're going to look at that very soon. So for sp2 orbitals, you only form 3 bonds, and the rest of the p orbital can be used for another overlap bonding. So this carbon that has sp2 hybridization will have a bond angle of about 120. So it has 120 degrees for all these 3 bonds of sp2 hybridized orbitals. And again, they are all degenerate orbitals. Let's look at sp hybridization of carbon. The same thing, you have 1s2, 2s2, 2px, 2py, 2pz. One electron from the s orbital will be moved into the pz orbital, and only two of the orbitals will be mixed, remaining two other ones that will not be used. So this will lead to 1s2, 2s1, 2ps1, 2py1, and then 2pz1. But the interesting thing is that it's only two orbitals that will miss, and that will produce what we call the sp orbitals. So that will only give us two bonds. And the bond angle between the sp orbitals is just 180 for the carbon. And then you have these two p orbitals that are hanging and can be used for what we call pi bonds. So these will be the sp orbitals and another sp orbital here. But the unhybridized, these ones were not mixed. The spy and the spz were not mixed. So they will be hanging around where the electrons will be floating. So this will be your typical sp hybridized carbon. So now let's take a look at examples of molecules in the hybridization states. So let's begin off with methane. So you have carbon that has 4 hydrogens attached to it, and we have to determine the hybridization state of this carbon. In order to do that, you have to count the number of atoms that is connected to. So if it's connected to 4 atoms or 4 groups, then it's likely to be sp3 hybridized. If it's connected to 3 groups, then it will be sp2 hybridized. 2 groups will be sp hybridized, and 1 group will just be no hybridization. So looking at methane, obviously that will be an sp3 hybridization. One other thing is that since we didn't look at oxygen, which is 8, when you hybridize oxygen, you have 1s2, 2s2, 2ps, 2py, and 2pz. Since it has 8 electrons, you're going to have something that looks like that. So when there's a hybridization, there's a movement of electron to one of the p orbitals. Depending on what type of hybridization, you will end up with 2s1 electron mixing with 2p. So let's say the oxygen is sp3 hybridized, then you're going to have all these orbitals mixed together. So you're going to have all of them mixed together, but then 2 of them will have lone pairs. So when you mix this together, you're going to have 4 bonds. Oxygen will have 4 bonds, but then 2 of them will be lone pairs. So usually we put just the lone pairs on the oxygen. So let's take an example in which you have oxygen and carbon. So you have this structure right here that has these carbons and oxygen. So let's see how the hybridization state of these atoms look. So if you look at this atom carbon right here, I should say, what is the hybridization state of this carbon atom? First, you have to count the number of units it's connected to, and it's connected to 3. And because it's connected to 3, this will be an sp2 hybridized carbon. Let's look at oxygen. So oxygen is connected to just carbon, right? It's connected to carbon here, and also it has connection to this lone pairs of electrons. So it does have 3 connections, 1, 2, 3. So that will also be sp2 hybridized. Now, if you look at this carbon here, it's connected to 4 groups. This carbon, these hydrogens, and therefore this carbon will be sp3 hybridized. Let's take another example in which you have nitrogen. Nitrogen connected to these hydrogens. You can tell the hybridization state by just looking at how many groups it's attached to. So you have 4 groups, these 3 hydrogens, and the lone pair. So this will be an sp3 hybridized atom. So this is how you're able to tell the hybridization state of a lot of these compounds. All right, so now that we've understood what hybridization is, let's look at how bonds are formed using these hybridized orbitals. So let's take an example when it comes to, let's say, a carbon-carbon bond. So we look at ethane. So how would the ethane molecule be formed? So looking at the ethane structure, what are the hybridization states of these carbons? Of course, this is going to be an sp3 hybridize. That's an sp3 hybridize because they are attached to 4 groups. So looking at how the hybridization happens, you have the sp3 hybridized carbon that has these 4 orbitals sharing 109.5 degrees angle. And each one of these orbitals will have the electrons that have been mixed. So they have the same energy. Now you have another carbon that has almost the same structure. So you have another carbon here that has another sp3 hybridized state. And it has these electrons in its orbitals. So what happens is that during the reaction, of course, these electrons can overlap through what we call a covalent bond. Okay, so they will overlap and form a sigma bond. Sigma bond. So sigma bond is usually formed with a head-on or overlap. So these 2 orbitals will have a head-on overlap. Now, when that happens, there will be hydrogens. So these hydrogens have only one electron in their shell, and they want to complete what we call the doublet configuration. So they also overlap using a sigma bond. The same thing will happen here. The hydrogen will overlap here too, and it will do the same thing with all the other orbitals. And that is how you're going to form your ethane gas. Now let's take another example and look at how ethane, which is double bonded carbon, is formed. Now if you look at the ethene structure, you can tell that the carbons in this structure are sp2 hybridized. So sp2 hybridized, like we mentioned, have these carbons having these orbitals that are 120 degrees away from each other. So you have 2 of these carbons with these orbitals at 120 degrees to each other. And inside of these orbitals, you find each of the bonding electrons. So you're going to have these bonding electrons distributed in the orbitals. Now, the interesting thing is that each of these has a p orbital that is not hybridized and sits perpendicular to the hybridized orbitals. So during the covalent bond formation, there's going to be a head-on overlap of these 2 sp2 orbitals. So there's going to be an sp2 orbital from here and sp2 orbital from here overlap. So that bond is going to give us a sigma bond because it's a head-on bonding. Now the other thing is that the p orbitals, the 2 p orbitals, which are not hybridized, let's say the 2pz, will overlap with each other, and that will form the second bond, and that bond is what we call the pi bond. The pi bonds are weak because you can see it's just a virtual overlap. It's not a head-on, it's a lateral overlap. They're also long in nature. So what happens is that they tend to be, the overlap of this tend to be a little longer than if you had just a sigma bond. But because it's a double bond overall, pi bonds are shorter. So pi bonds are short. So because of that, you tend to see that the double bonds pull these carbons closer to each other. So double bonds are shorter than just single bonds. So this is going to give us a carbon with a double bond bonded to another carbon. And as we mentioned earlier, these orbitals can overlap with hydrogens, and that will give us the ethene structure. So you're going to have your hydrogens bonded to these carbons. So lastly, we're going to look at how triple bonds are formed. So triple bonds are formed between two carbons, or sometimes even between nitrogen and a carbon. So let's see how these triple bonds are formed, especially in the case of ethane. So looking at these carbons in the structure, they are attached to one unit and the other one here. So that gives us an sp hybridized, and that's an sp hybridized. So based on our knowledge, we know that sp hybridized carbons only have two orbitals that are bonding, and they are 180 degrees to each other. And the other p orbitals that are not used in the hybridization sitting around on this carbon in different directions. So you have one sitting like that, going perpendicular, and one going vertical. You have the same type of carbon, on the other hand, with two orbitals. And of course, the p orbitals are hanging in the same way, perpendicular and then horizontal. So what will happen is that the electrons that are found in these hybridized p orbitals, so these are the sp orbitals. So you have an sp here, sp over there, and sp over here. So these sp orbitals have electrons in them that can engage in a sigma bond. So looking at that, this sp will overlap, I should say, with that sp to form a sigma bond. Now, the next thing is that these p orbitals will overlap to form a pi bond. So these will overlap to form a pi bond. So this will give us the carbon has a sigma bond, and then you have one pi bond at the top and one pi bond at the bottom. And these orbitals here will overlap with hydrogen as usual to form the ethane molecule. So this will give us that structure. So the bond angle here is about 180 degrees. The bond, because of its triple bond, is very short and very strong as well. So because you have triple bond, it makes the bond between these two carbons very short and also very strong. So this triple bond is way stronger than a single bond. You can also imagine that double bonds are stronger than single bonds. So that completes this section or this video on atomic structure, how bonds are formed.